is a beautiful building, isn't it?
Yeah, this I've been here for 12 years. This was the site where it all really started. You know, this is the Clark Center at Stanford. It's not one department. It's many departments all intermixed, and so it's a place where people from different fields are naturally next to each other, and that was very valuable.
Yeah, it helps, no, for research.
It does. It stimulates people's thinking. It helps them enter into new, uncomfortable areas where the path is not so clear, I think. And the environment does matter. Yeah.
I've heard something peculiar about you, that you are able to read in blocks.
Yes, the reading, for me, it was my main hobby as soon as I could read very early in life, and so I read all the time. But one thing I noticed, not only do I happen to be able to read very quickly, but I remember also what I read almost word for word. It's an interesting brain property feature.
And do you have any idea, or at least an hypothesis, why the structure of your brain stores memories better than other brains?
You know, one thing we all know is that what we like, what we're passionate about, what arouses our interest, we remember that better. And for me, my unique memory or unusual memory skills are only related to words and structures and sentences. I don't have a particularly good memory otherwise, except for sentences that I like the flow of language, I like the rhythm of language, and I think it's because I like it so much that it sticks. But it's a common thing, I think. For people who love numbers, I think they can remember numbers very well.
I was asking this about the structure because this idea that not all brains are equal is very interesting for something that you do research, mental diseases, no?
So we think about this a lot, the nature and the source of individual variability. And we can study that in animals too. You can have a whole set of animals, brothers and sisters to each other, mice or rats, you know, same parents, same environment, growing up, very similar genes, and yet they have very different behavioral traits. One will prefer risk, and one will prefer safety, and these individual traits and their cognitive performance is different as well. But the brain structure, as far as we can see, is the same. Now, that may be that we don't understand the structure well enough, what to look for, or it may be that there's something else that's not physical that's different about the brains, something about the dynamics, the activity patterns that flow through the brain may have a different form.
Yeah, something that maybe we are not able to measure yet.
Right,
no?
that's right.
Because it's very interesting your profile, because you do very basic research, but you also see patients.
Yes. Yeah, I'm here in this basic science building most of the time, but then I have a half-day clinic, you know, once a week or every couple of weeks, and I walk over to clinic, I see patients, I give medications, we do some brain stimulation, electromagnetic brain stimulation treatments. And yeah, I focus on depression and autism. And it is different from the basic science. But I find it refreshing. It's nice to go and do something very different. But it also helps because in the lab, you know, we're studying how the nervous system works and how the brain works, and it can be a good clue to see how it fails to work and how it you know, how pathology or psychiatric disease arises. That's good for helping the patients, but it's also good for helping understand the normal brain.
And with severe depression, the depression that it's not caused by the environment, it's caused because of the structure of the brain. What have we learned in the recent years on this?
You know, we would love to be able to point to something on a brain scan and say, this means that you're vulnerable to depression, or this means you'll benefit from this kind of medication. But we're not there yet. Right now, in the study of depression, the treatment of depression, there's no reliable, measurable that you can point to and make a diagnosis or guide treatment right now. But so that makes psychiatry and depression very different from other fields of medicine. But one goal we hope to achieve is to get us to a point where we know one part of the brain, one structure, one measurable pattern of activity will help us diagnose and treat disease someday.
Yeah, because this idea that you are depressed, you have low levels of serotonin, this is too simplistic, no?
It's too simplistic, and it's not valuable at the single person level. So there are these big population studies, and you can pick out things like this, where if you average dozens or hundreds or thousands of people, that yes, there is a difference in a serotonin level or even a structural thing, but it requires very large populations, averaging them all together. Nothing works at the single person level, so you could point to a person and say, this is your diagnosis. We can't do that yet.
And maybe with some mental diseases, because scientists, you're able to measure molecules, you're able to measure with fMRI big areas of the brain, but all this circuitry, it's unknown yet. And here is where it comes your marvelous technique of optogenetics, yes. No?
Well, this is exactly right. In between these two extremes lie the circuits, and this is what a lot of scientists and psychiatrists think now, that the answer lies at the circuit level. And that is indeed what optogenetics does, is it gives you access to the circuit level and what matters, what causally matters at the circuit level.
Because optogenetics is kind of crazy if you think about the idea. You take some genes from algae, you include them in specific neurons that create channels that are sensitive to light, and you're able to activate or deactivate specific neurons. How you came up with such an idea?
Well, it's something people have been trying to do for a long time. So this is I certainly, our group, none of us were the first to think about it, not the first to try it. Many people had tried to do something like this before. The first person who thought that light might be made useful to control neurons was Francis Crick of Watson and Crick. Yeah. And he didn't have an idea for how to do it, but he said, wouldn't it be great if we could control individual kinds of neurons, and maybe a good signal would be light. And light is fast, light can scatter into tissue non-invasively, and so it has some useful properties. But he had no idea, Crick had no idea how to do it. And what we and many other people did was to try to make neurons, which are in our brain. It's very dark in there. Normally there's no light at all there, so they don't respond to light. Our brain cells don't respond to light at all. They don't care, light, dark. But how can you make them respond to light and make it easy to target that responsivity to one kind of cell or another? That was the key challenge, because the brain is like a whole tangled mass of pasta. You know, there's neurons that do completely different things, are right next to each other. Their connections are all intermingled. And so unless you can target the light sensitivity to the kinds of cells you're interested in using genetic tricks or wiring information, then it's hopeless to figure out what actually is causing brain function and behavior. So that was the challenge. How do you make cells sensitive to light, but in a targetable way, to target the kinds of cells you want? And many people tried, and right here between 2004 and 2005, we were able to make a system that worked. First in a dish, just in a plastic petri dish, and that was in 2005. And a lot of people rightly criticized it at the time. They said, "Well, it's just in a dish. Yeah, this will never work in a behaving mouse or a mammal of any kind." And that was hard. Indeed, it took us about 4 more years after that to invent all the other parts of what became optogenetics. But by 2009, we had all the pieces together, and it was working.
And now lots of neuroscience labs are using this technique, no?
Oh, yeah.
Because it's a great tool, first for research, no? What kind of experiments can you do with optogenetics?
Well, it's amazing how many different kinds of experiments are being done. Thousands and thousands of labs around the world have found it useful studying every kind of neuron from every kind of animal. In my own lab, we're working with rats and mice, and we're looking at motivation and reward and anxiety. And we're looking at these basic mammalian drives and inhibitions that guide behavior. But across the world, so many other applications have been carried out. People have studied everything from memory to locomotion to social behavior, drug addiction, studying where brain waves come from, these oscillations that happen in the brain. Everything you can imagine has been studied.
Because you mentioned anxiety, and I don't know if it's because we were said about depression before. It's something that starts in the emotional side of the brain, and it affects maybe your cortex or your interpretation of the world. Anxiety how it seems the contrary, that it's something happening around and it affects our emotions, like it was in different directions. Make it sense, or?
Yeah, anxiety, the way we define anxiety, it's different from fear. Fear is when there is a threat right in front of you and then you react. That's fear.
Okay.
Anxiety is when there is no immediate threat, but one is apprehensive that one might be in an environment where there would be a threat potentially. And so you're right, it is a signal coming from the environment, but it's not an immediate danger. It's more of it's both. It's the environment and your own perception of the environment that work together to create anxiety.
And optogenetics, as a tool, you can study these communications of areas of the brain,
yes,
for example.
Yes.
No?
So, and we used optogenetics to understand how anxiety is put together. And let me explain what I mean by that. So we've all been anxious. We've all felt anxiety. But it has many parts to it, many features. So when we're anxious, our heart rate goes up and we breathe faster. And it feels bad also, which it may sound obvious, but it's not. And also we become less willing to put ourselves in risky situations. So there's a behavioral component and a physiological component and an internal subjective component. All these different parts of anxiety, all are part of the state. And what we did with optogenetics is we figured out how each of those features, each of those components of anxiety are assembled, put together from across the brain and bound up into a coherent state. And we could only do that with optogenetics. There would be no way to have the specificity without optogenetics.
How cool. And we said optogenetics is a great tool for research. Is it ready yet for therapeutics? Are you aware of any clinical trials? Or?
Yeah, to my knowledge, nobody is going into the brain for psychiatry or neurology with direct optogenetics in the sense of putting in a gene from algae into the brain, which I think is fine because what we're already seeing is clinical trials, therapeutic clinical trials based on optogenetics, but not using optogenetics, instead guided by the knowledge that optogenetics gave. And I'll give you an example. So there was a very interesting study on cocaine addiction. In 2013, there was a paper that found there was an area in the front of the brain that in rats, if you stimulated this, you could make cocaine-addicted rats not care about cocaine anymore, which was very interesting, surprising. It was published in a great journal. It got a lot of attention. I was not involved in that study. That was a scientist named Antonello Bonci who did this work. But it was so interesting that the optogenetics had given him this causal insight that driving activity here in rats turned off cocaine addiction, that they then did a clinical trial using that knowledge, that causal knowledge, in people. But they didn't use optogenetics because that would involve putting a gene into the brain from algae, and it would involve putting a fiber optic into the brain, which you could do, but turned out it didn't need to do that because there already is a non-invasive brain stimulation method called transcranial magnetic stimulation, or TMS, which is used clinically for depression. I've used it many times. Many groups around the world use it. It's a non-invasive way of stimulating the brain. And what they did, using the optogenetics knowledge, they took a large group of cocaine-addicted human beings and split it into two, and half of them they gave this TMS to the same homologous, similar brain area that the animals had had, and they had a control group that didn't get the treatment. And they saw a very profound reduction in cocaine-seeking behavior in the people, the human beings. So that's an example of the optogenetics guided clinical trial, which has already happened.
But do you envision applications, therapeutic applications of optogenetics, probably if it's safe and everything?
It could happen. I think the way it would first start, I'm not doing that in my lab, but the way it could start would be maybe in the peripheral nervous system, you know, in the arms and legs, maybe to counteract pain, or some people are thinking about vision for in the retina for certain kinds of blindness. Could you confer light sensitivity onto the retina of a blind person? And I think that's reasonable to look at in these areas of the brain that we understand a little better than the deep brain.
Another great technique that you've created is clarity.
Yes.
You make transparent brains. So how can you do something like this? And what's useful for?
Well, one thing we noticed, this was after we had solved the key problems with optogenetics, was we still wanted to know more. We wanted to know a lot more about the brains that we were studying, and particularly we wanted to know the wiring. Because we knew that there were neurons. Optogenetics had taught us that there were certain neurons that controlled behavior. But to get to a deep understanding, we wanted to turn the brain into a circuit diagram, like opening the book and seeing how a circuit's wired up. And we weren't getting that information alone just from optogenetics. Now, it's pretty hard to get the wiring out of a brain, and the reason is, first of all, like I mentioned before, that all these connections are all a tangled mass of spaghetti strands, and it's very complicated. But also, the brain is not transparent, and you have to take an animal and you have to cut the brain into very, very thin sections, thousands of slices, to see deep into the brain. And that was a big problem because you're destroying the tissue when you cut these slices, and you lose the three-dimensional information that you most want, the global wiring information. So what we were able to do was to turn the brain transparent, and this was actually allowed us to keep the brain intact and to not have the need for slicing or sectioning. And that was why we developed the method. And it's turned out to work together with optogenetics very well.
Wow. It's impressive because, of course, we still a lot of things to learn about the brain, but it seems that we are moving from neuroscience to neurotechnology. We are able not only to study the brain, but to manipulate it. You mentioned TMS, now optogenetics, clarity. Are we really in this moment moving from science to technology?
You know, I certainly feel that excitement, but I also, if you take a broad look at the history of neuroscience, it's actually always been driven by technology. So Santiago Ramon y Cajal, for example, you know, his innovation and his Nobel Prize was ultimately technology driven. You know, there was a method for looking at individual cells with very high resolution that together with his brilliance and his rigorous and systematic style of science, allowed him to gain deep insight into the brain. And that ultimately was technological. It was a neurotechnology in the early part of the 20th century and late 19th. And we had, and again in mid 20th century, Hodgkin and Huxley, these were the ones, and up until 1950, 1960, they worked very hard on understanding what an action potential is, this little blip of current that is the currency of information flow in the brain. And they were engineers, and they built beautiful, for the time, devices to let them record the signal. So I think the history of neuroscience is of neurotechnology. But I also agree with you that there is a particular excitement now because there are so many new kinds of insight we've been able to acquire. The intactness of the brain, its function, the cellular resolution information, during complex behaviors. This is probably a unique time to be a neuroscientist when I think we're finally able to move toward understanding the entire brain as an intact functioning system.
No, of course. Technology, I mean, Santiago Ramon y Cajal is a clear example, drives science and knowledge. But now there are techniques that are manipulating the brain. And many people are talking about brain enhancements. You're able with your rats to affect perception, actions, feelings. Do you think we'll be able to manipulate the brain to enhance some of their properties? To get a good memory like yours?
Well, that's a very interesting question. I think it is theoretically possible, and it does raise ethical issues and philosophical issues that have to be considered. In some ways, it's not a fundamentally new question. We've always been able to enhance the brain. When I drink coffee, I'm more alert. I remember things better. But the speed and precision of optogenetics does create a new kind of situation. I can have an animal, a rat or a mouse, and I can affect what it wants and how much it wants it. I can turn up or down its motivations, its drives, its functioning, alter its memory up or down. And so this does raise ethical questions, and enhancement is something that's widely discussed. Optogenetics, fortunately, it's not so easy to do in people, and that means we don't have to worry maybe right now about this issue. Other technologies are more worrisome because right now you could do things, and this was why people worried about cloning, human beings, and why they worry about CRISPR-Cas and all this, because these are, equally dramatic findings, but more urgent and pressing because they could be applied right now. With optogenetics, we've got a little time, I think, because there's so much to understand yet.
Well, optogenetics helps you to understand how to improve these brain functions, and you use the word worry instead of excitement. This is tricky, isn't it?
It is tricky. It is tricky. And even if it's never directly applied in a unethical way to people, I think there are still philosophical implications. It does make the point very clear, which maybe we knew already, but it makes it unambiguous that who we are in terms of our memories and our skills and our priorities and our inclinations, all these parts of us that create us, these are all due to the activity patterns happening in individual neurons in the brain. And that's a philosophical point which is now very clear.
Wow, no, this is one of the biggest mysteries, no? So if we move to something more innocent, not talking about enhancing brain, but even only to understand them. It's not a small question. What are these mysteries that you think we are kind of little close to answer?
There are certainly many little mysteries. I think there are big mysteries, and there's everything in between. With the heart, it's very clear what the heart is doing. It's pumping, okay? And so we know when it fails to pump, we can model that, we can measure it, we can say, okay, there's less blood coming out with each stroke of the pump, and that tells us what we need to change therapeutically. We have nothing like that in the brain. We don't really know what the brain is trying to do. We don't have a model of its function. We can see it uses oxygen and blood, and it generates behavior, but we don't really know what the functional units are. And we know it's made of tens of billions of neurons, but we don't know, is each neuron important, or do they work in groups of 10 or 10,000? Is the functional group, if there is one, is it wired up in a particular way? Does it have some structure? These are all, I don't know if these are little or big questions, but we know none of this for the brain, nothing.
Wow, and then what do you think when you hear people talking about Neuralink or moving the consciousness into a computer, all these extreme neurotechnology advances that they say that it's exponential, the knowledge that we have and will achieve in the next 10 years. What do you think about these claims?
There's no doubt we're in an exciting time. We're in a time of exponentially accelerating technology and capability. I completely agree with that. And I think that acceleration will help us get to these answers more quickly than before. But just that capability, what our computers can do now, is not enough by itself. It's not, right now, nobody could say, here's how I'm going to put a conscience into a computer. Even if they had all the computational power in the world, nobody would know how to do that. And so we're still missing the understanding that would make that possible. But of course, the computers help us greatly, and that's an increasingly important part of neuroscience. So it's another reason why it's an exciting time to be studying the brain.
No, there are so many things. I was in Berkeley the other day with a friend of mine called Carmona, who's working with neural dust.
Oh, yeah.
They're putting sensors in between neurons.
Yeah.
So what do you think about technology like this?
Yeah, I was in Berkeley just a few weeks ago. I talked to Jose Carmena and his group. I think it's very interesting. Again, all of this is risky. What we do is risky. What they do is risky. But it's the right time to take risks. And time will tell what works and what doesn't. But they have a wonderful group up there, and I'm sure they'll be successful.
And any patient that you've seen lately that makes you some insights or make you think about something interesting?
You know, patients always surprise you. You know, you think you understand, and in psychiatry particularly, you know, you can see the same patient in your clinic for months and years even, and you can think you understand them, and then the world changes, something happens, and you know, I had a patient, still do, a patient of mine with autism spectrum disease. He's an adult, but he has autism traits, and that means he doesn't understand social situations very well. He can talk, he can communicate with me, which some autistic patients can't do. He can talk, but he doesn't understand conversation. He would look at us talking, and he would have no idea how one of us knows when to stop and the other when to start. It's like a foreign language to him, that social code. But I was helping him over years and years, you know, some behavioral tricks and also some medication to reduce his anxiety and other things. And he was doing pretty well. And then just about 6 months ago, everything went bad again for him. You know, maybe it was a phase of his life that was changing, or something that happened in the world. A lot of strange and confusing things happening in the world as well, and maybe that was part of it. But all of a sudden, he felt that he couldn't function in the world as he had been. He became confused and worried, and felt that whatever mastery he had achieved was no longer relevant or valid. And this is very interesting to me, because psychiatry, it's not just what's going on in the body like so many other fields of medicine, but it's the interaction between the body and the world and other people, and that's where the disease often is. And so you have to think about the world and the patient, and how the patient constructs the world in their mind. And it's this just became clear for me over the last few months.
Yeah. No, it's obvious that in mental disease, it's the brain and it's also the environment. But this autistic brain of your patient has clearly something different from a brain like mine on yours. And science, for the moment, is still not able to see.
Right.
There's no methodology to see what's different, no?
There is no methodology, that's right. And so he looks, you know, if you looked at a photograph of him, he would look normal to you. If you did a brain scan, the highest resolution MRI or PET, EEG, all that would look completely normal in him. You you would have no idea that he had autism. And so we have no diagnoses except by talking to our patients. That's how we diagnose right now.
So this is the importance of science and research, to create more technologies like the genetics or clarity to understand. Without this understanding, it won't be impossible to treat.
That's exactly right. So that's why I spend most of my time here in the basic laboratory, because that's the real limiting step. I could treat all the patients I wanted in the clinic, and I might help them a little bit, but really where I'm most needed is here.